Let's talk about navigation. Well, navigation is made up of the word navis, that is ship, and agri means to direct. Basically, this is the process of directing the movement of a ship or aircraft from one point to another. Well, this is both art and science, which involves conducting a ship safely to its destination. So, if this is a point A and this is point B, the ship has to go from this point to this point. That is navigation, and it has to go safely, right? Then let's talk about the definition by various authors. So, navigation is a purposeful control of motion from one place to another place. That definition is given in Principle of Navigation by B.W. Anderson. Then there is a famous author, Baldwin, and it says the process of planning, recording, and controlling the movement of a craft or vehicle from one place to another is called navigation. So, practical navigation. Practical navigation is the answer to many questions like which way to proceed, and that is we figure it out from passage planning. Then as a navigator you should also know where I am. That is achieved by position fixing. Then which direction to steer, that is the chart work we need to allow for the courses. And last, and that is not the least actually, do I know what exactly is going on, that is situational awareness. Right. So the terms which are describe the movement at sea, that is a starting point, is called departure point. Direction of movement, we can call it course. The distance run is nautical mile, and we studied that 1 nautical mile is 1852 meter, and 1/10 of the nautical mile is 1 cable. So what a navigator needs to know on a nautical chart? On a nautical chart, actually, you should know the shallow water area, the areas where there is less water, obstructions, if there is any obstruction, there are some hazard, what is the location of harbor, and other nautical related information. That is what a navigator desires to have on nautical chart to assist him or her for navigation. Now let's talk about Earth. To understand the navigation, chart work, and other tasks which are associated with the navigation of a ship, it is essential to understand the shape of Earth. Well, we can say that Earth is an irregular shaped lump of rock that looks like an oblate spheroid. So here, have a look here. Earth is having equatorial diameter this way, and this is the polar diameter. All right, this is North Pole and this is South Pole. So Earth looks like a oblate spheroid. Now you may wonder what is oblate spheroid. So if you are having a sphere, and how we call it a sphere, that there is a 3D shape which is formed by rotating a circle on its axis. So this is the circle, and the circle will be having this axis. Let me choose the color like this, and if I rotate the circle like this, I am going to get the sphere. Then we have a term spheroid. A spheroid, suppose this is an ellipse, and ellipse will be having two axes. One will be the minor axis, this one, and one will be the major axis. So 3D shape formed by rotating an ellipse on one of its axes. So if I try to rotate the ellipse along the minor axis this way, I have the shape called oblate spheroid. And if I rotate this ellipse like this, then I will have prolate spheroid. Of course, we are not going to study this prolate spheroid. We are going to study only the oblate spheroid. Well, sometimes we use the term ellipsoid or spheroid. They are, for navigation purpose, they are interchangeable term. Now, this is very important. We need to understand what is the compression of Earth. So, the ratio between the equatorial and polar radius and the equatorial radius. Suppose this is the equatorial radius, right, that is A, and this is the polar radius. The difference between the two are divided by equatorial radius, and these values are given here. A is 6378 kilometer, B is 6357. So the difference is 21 divided by 6378. So I get 0.033. Now imagine if the Earth was spherical, then A would have been equal to B and the compression would have been equal to 0. But now the Earth's compression is not 0, rather 0.0033. So let's talk about important facts about Earth. So there are 70% of the Earth surface is covered by water, and there is a force of gravity. You must be remembering this, Mr. Newton. All right, the force of gravity pulls every object towards the center. Earth revolves around the sun in a fixed orbit. So this is the fixed orbit, and here it is sun. Earth is going to revolve like this, and also Earth rotates about its axis. So this is a rotation and revolution. Now, reason for bulge at the equator: because of the gravitational pull on the water level, and there is a centrifugal force due to the rotation of Earth. So the final shape of the Earth is geoid. Shape of Earth with respect to mean sea level is called geoid. Right, have a look in this diagram. This white color, that is geoid. All right, and this red color, that is spheroid. Earth's surface could be a little bit up and down, and there could be sea. So difference between ellipsoid and the geoid is called geoid height. So here this is the geoid height, which is about 100 meter below and 85 meter above mean sea level. This height can vary. Well, many different spheroids are used for position fixing on nautical charts. One is World Geodetic System 1984, and there is something called European Datum 1950. Basically, datum is a mathematical model of Earth which is used for position fixing. Now, let's understand. Reduce the Earth to the size of a tennis ball. So, this is your Earth and this is your tennis ball. And you may be wondering which one is much more smoother. Of course, Earth is much more smoother than the tennis ball. All right.